In this video, we begin looking at finding volumes of objects. There are three different methods that we're going to be exploring in section 2.2, slicing, disks, and washers. The first method, which is the subject of this particular video, is slicing. Well, you can't see it here too well, but if we take a flat plane, like a piece of paper, and slice it through this particular object, no matter where we slice it through this object, we're going to get the same cross-sectional area that looks like this, like a semicircle. And this is the axis of this object, and so we call this a cylinder. This line here is the axis of the cylinder. And when we slice the plane perpendicular to the axis of the cylinder, no matter where we slice the cylinder, we get the same cross-sectional area, which in this case is a semicircle. That means that we have a cylinder. Well, a cylinder is very easy to find the volume of. In fact, most of the geometric formulas that you're familiar with are based on that of a cylinder. So a typical cylinder is a can. But a box, technically speaking, would be a cylinder. And so to find the cross-sectional area of something like that, we take the cross-sectional area, in this case it's a circle, times the height of that object. So we have the cross-sectional area, which will probably be in terms of x, times height. Well, what about the box? Well, the box, we have the cross-sectional area, which would be a square, times the height of the box. So in either case, what we're looking at is we're looking for cross-sectional area, a sub x, some formula. Again, here in the can, the cross-sectional area is the area of a circle. Here it would be the area of a square. We take the cross-sectional area, multiply it by the height of that cylinder, and we have the volume of the cylinder. So that's a very simple case. And as I said, most of our geometric formulas that we're familiar with are based on cylinders. But what happens if we have an irregular area, such as this particular object right here? I also like to think of a loaf of bread, an irregular loaf of bread. So if we were to slice this object anywhere, the cross-sectional areas are not going to be the same. All right, so the cross-sectional area here would not be the same as the cross-sectional area here. That shape may be different, okay? Might be a slightly different shape. So therefore, it's not just a matter of taking the cross-sectional area and multiplying it by the height. So what we do is we do something similar to what we did when we're finding the area under a curve. We take that area and we divide it up into a bunch of rectangles, all right? So what we're going to do is we're going to take this volume and we're going to divide it up into a bunch of smaller little slices. That's why this is called the slicing method. Again, think of a loaf of bread. If you wanted to find the volume of a loaf of bread, what you could do is you could slice it into a bunch of slices, find the volume of each one of those slices of bread, and then add all of those volumes together. And that's essentially what we're doing. So we've created three slices in this object, S1, S2, and S3, creating three pieces of bread. So again, use a little bit of an imagination. You've got one piece of bread, two pieces of bread, three pieces of bread. Now, clearly, the front end of the piece of bread and the back end are not exactly the same. So this is going to give us an approximation. We take the cross-sectional area of each slice of bread, we multiply it by the length of that bread or the width of the bread, and then we have the area of one slice. And so you have the area of slice 1 plus the area of slice 2 plus the area of slice 3. Take all of those, multiply them by the height, assuming that each one of them has the same height. So each one of these distances here is the same. So the thickness of each piece of bread is the same. Well, basically what we've got going here looks kind of familiar. Looks like we are taking the summation from n equals 1 to n slices of bread times the height. And that is exactly what we're doing. We are creating ourselves here a Riemann sum. And so here we have an approximation. The volume is approximately equal to the sum of the cross-sectional areas of each slice of bread, and delta x now becomes the thickness of each piece of bread. Well, just like with the area under the curve, the smaller we make our rectangles, in other words, as delta x, the thickness of each rectangle approaches 0, or the number of rectangles approaches infinity, we get the exact area. And so we do the same thing here. We let n approach infinity, which means the number of slices of bread is approaching infinity. And as that happens, we get the exact area, volume of that loaf of bread. And so that takes the shape of an integral. So volume is equal to the integral from a to b of a cross-sectional area times dx. The key to using the slicing method is you must be able to determine the cross-sectional area. If you cannot find the cross-sectional area, this method is simply not going to work. So the procedure for doing this is examine the solid and determine the shape of the cross-section of the solid. It is often helpful to draw a picture. Determine a formula for the area of the cross-section. Again, that's the important part. Integrate the area formula over the appropriate interval to get the volume. So the first problem that we're going to do here is going to be deriving the formula for a pyramid. And so, again, the first thing that we need to do is, can we come up with an equation for the cross-sectional area? And so the cross-sectional area is represented here by S. A is one of our cross-sectional areas. S is the other cross-sectional area. S squared actually would be, S times S would be the cross-sectional area. What we know is that the base is square. So this area of the base is simply A squared. The area of this cross-sectional area is S squared. So we can figure out the cross-sectional area, but the cross-sectional area is continually changing. It's not constant because we have a pyramid. Okay, the cross-sectional area of A is not the same as the cross-sectional area of S. So no matter where we position S within this pyramid, we need to be able to figure out a formula for its cross-sectional area. And so over here, we look at how we can do that using similar triangles. So we can simply say S is to X as A is to H. So this distance here is to this as this distance here is to this. We're just creating a proportion. S is to X as A is to H, solving that for S. S is equal to AX over H. Now, S is just the length of the side. S squared is the cross-sectional area. And so that's what we've got over here. So S squared gives us the cross-sectional area for any side length S in this pyramid. All right, well, that's pretty much all we need. We need to know the bounds of integration. The bounds of integration are going from 0 to h, h being the height. So when the height is 0, all the way up to whatever h is going to be. And so now we can set up our integral. And so we have the integral. Here's our basic formula. And so now all we need to do is plug in our bounds of integration, 0 and h, and then plug in our cross-sectional area formula, which is ax plus h squared. Now, what I like to do when I'm integrating is get the constants out. Move the constants out of the integration problem. It makes it simpler. A is a constant. H is a constant. They're both being squared, so I remove them and put them over here in front of the integration sign. That just leaves me with the integral of x squared, which is easy to integrate. We get 1/3 x cubed times the a squared over h squared, evaluated from h to 0. So plugging in h, plugging in 0, we end up with 1/3 a squared h. And that would be the formula for a pyramid, volume of a pyramid for any base A. All right, so that's it for this video. That is the slicing method. There's not going to be too many homework problems on the slicing method. I just wanted to introduce that. The next two methods are a little bit more interesting, and they involve basically circular regions and revolutions. So that's it for this video.